Yeah, I think. All right, guys. It's it's good to have have everyone here. Uh, we'll welcome everyone to another gathering of the community of practice in engineered solutions hosted by Smart Grid CRC. I am Arun. I work for Advanced Precast. We are in the precasting business, and it's great to have a precasting presentation that I'm lucky to chair. It's great to have all here once again as another opportunity to bring together industry experts, researchers, and the wider construction ecosystem to discuss ideas, breakthroughs, and best practices around concrete solutions. Let's not beat around the bush and jump straight in. Today we are going to talk about next generation precast concrete wall and column connections for multi-story buildings. That's mouthful. Uh, we have got some interesting topics today. What are the precast wall and column connections? Why is there a need to improve efficiency in these connections? What's the state of the art? So on and so forth. We are fortunate to have two fantastic speakers lined up, one from industry and one from academia, bringing in a wealth of knowledge from both sides of the fence. A few housekeeping rules before we start. This session is being recorded and uh, sent to all the registered attendees. So if your friends who are not attending, feel free to share. Uh, we will really appreciate if you can keep the mic off while the presenters are presenting, and we'll hear from each speaker in turn, and then open the floor for questions. But if you have a burning question during the speak, please pop it in the chat box or raise your hand. Uh, please pop it in the chat box or raise your hand and jump in once the presentations wrap up. That being said, without further ado, me invite the first speaker, Andreas Boomkamp. Andreas from PSA. He joined PSA recently as the business development manager in New South Wales, bringing 20 plus years of engineering experience from Germany, the United States of America, and Australia. He's a chartered structural and civil engineer. He has done it all: product development, tech documentation, and shaping the industry through standards Australia committees. Is all about smart solutions, strong relationships, and raising the bar in prefabricated concrete and reinforcement systems. Over to you, Andreas.
Thank you very much, Arun. I will share my screen. And yeah, thanks for the invite to this presentation. I hope you can all see my screen now, and I will start with a little bit of a problem statement. Where did we come from to come to this project, or where did the project group at this time come from? Because I only recently joined, as Arun already mentioned, and then I will pass it over to Scott to talk a little bit more about what was done in research. So yeah, works great. Where we really started, or where the project group started, was looking at traditional ways to connect precast, specifically here panel-to-panel connections and high load-bearing panel-to-panel connections, where you have two options that both don't look very nice and both are not very nice from an engineering point of view. You have the cast-in plates that we are showing here on the left. There are two screws in there or bolts in this, but they are really just temporarily. Mainly the load connection here is the load bearing connection here is a welded plate that is welded on two plates that are cast into concrete panels. On the right side, you see a wet joint, which means that you have reinforcement bars coming out of the panels that you want to connect. You're putting additional reinforcement into an open joint that you leave there, and you're casting it later on. Both of these have significant disadvantages. First of all, on the left side, welding in general is something that we don't really want to see as much on, I say, modern work sites. You want to weld it as much as you can. It has issues with welding at heights. The quality is really reliant on the skills of the worker and even on the daily form of the worker. It is a complicated QA process where you can't really make sure that the weld quality is always right. The surface finish is also very questionable. So you have to grout over these panels later on, but sometimes it's hard to get that right. There are bigger areas later on in the panel that will have a different color, and the grout could also come out over time. On the right side with the wet joints, you're introducing on-site formworking again to a site where you really wanted to avoid it. You probably chose precast because you don't want to cast, or you don't want to put any formwork on site. You now also have to introduce reinforcement again. and you have to pour on site again. These joints will also be visible. Concrete color could be completely different from the on-site pour concrete towards the concrete that was used in the precast plant, and the surface finish will not be that nice. So that's the problem that started. In a group consisting of Swinburne, PSA, and Precast Concepts, the people had an ongoing cooperation over years where they looked at smarter connections. And from 2024 on, Smartcrete joined in as a funding partner of this group to look into these projects. I have all the people that are involved listed. I will not name them all, otherwise we're running out of time here. But yeah, Scott will present after me, and yeah, we are very thankful for Smartcrete to open this kind of forum for us, where we can make what we can do best, developing products, and we find the right people in the industry to join in with their expertise. A couple of words about who's PSA. PSA is a relatively young company, founded in 1996. It's almost 30 years now. Really started more in the area of the plastics. We are delivering solutions to precasters, and we have added a lot more load-bearing products in recent years, or recent decades, to be honest, where we're also doing lifting anchors. We're doing all kinds of precast connections. So we really fitted into the group here to look into finding a smarter way to connect. We're mainly supplying the precast industry, but recently we have also worked more with builders, precast manufacturers, form workers, and reinforcing contractors, whoever are the people that want to buy our products, but it all goes into precast panels. We supply a full range of consumables. From a footprint point of view, we are all over Australia, headquartered in Victoria. Myself, I'm sitting in New South Wales. So we have warehouses and locations in Sydney, in Melbourne, in Perth, in Brisbane, and in Townsville. From where we also do our prop hiring services. From the product range, lifting anchors, all kinds of connections, reinforcement connection systems, where we recently also added more and more products to, bar and mesh support chairs, all kind of architectural products for precast. And we also include what we call the AFA product, which is the Architecture Formliner Business Australia, separate company, but still under our umbrella, where we're making precast look even nicer than it already looks by putting all kinds of shapes in there that architects can dream of. So I hope that was okay as a short company introduction. Now to the product that we developed. So the product group, after looking at the two connections that I showed before, came up with a better solution, which we call the S connection. The S connection consists of two parts. The left side we call the male part, which includes a dowel, and we will look at this later. On the right side, the female part is basically just an empty opening that is formed in the panel where the dowel can go into. And I think best to show how it works is to actually show an animation that we prepared for this. I hope this is coming through. Where you can see the two parts. On the left side, as mentioned, the S connection male, and on the right side, the S connection female. And you can see here how after the lid goes off, a bridge, we call it bridge or dowel, comes out. These are two 24mm reinforcement bars welded together with two vertical bars, and on the other side it's just the empty connection. It is after the reinforcement is installed of the precast panel, our S connections are located, and really the most important part, and it will come also with a measuring tape hopefully soon. The really important part is obviously that the items are placed properly and in the right location. That's really the main thing that the precaster has to observe here, so that it later on works and that the dowel can slide into the opening. In this panel here, we have male connections on both parts. It could also be a male on one side and a female on the other. The reinforcement is shown. We test it, and Scott will talk about this later, with a U-bar above and beyond the connection, and also with some perimeter bars at the edge, and we will need the same reinforcement to get the capacities that we're stating. Here we're also using our PSA lifting anchors, the lift max from the lift max system. The items are transported to the side. All the lids are still on at this point on the male parts, so that we make sure that the dowel can't shift during the transport. Once the panels are at their final location and they are braced, hopefully with PSA braces, we are installing a backing rod in here as a seal. We are pulling the string out on the male part, and the dowel will automatically slide over. There are red marks on the dowel to ensure that we have a quality control and we can make sure that the dowel is all the way where it has to be. And then the seal can be closed to form a nice U so that we can grout from the male part and the grout will go over to the female part. And once you're done with putting some grout or some cement into the openings, there's really not a lot visible other than the two openings, and you have a very well engineered connection. Here you also see there's a corner connection available that we will see later on, where panels can be connected over the corner, or panels can also be connected straight panel to panel. Good. Up. Not sure what's happening. Yeah, okay, awesome. So Scott will talk later about the testing program and about the results from the testing. But as a result out of this test program, we came up with capacities here. Mainly the capacity of one connection is 195 kilonewton in lateral shear. The lateral shear is the main load that we see in these kind of panel-to-panel connections. It's the capacity that people require, which is quite similar to the larger weld plates, really, which is what we wanted to achieve. Multiple items, multiple connections can be placed on top of each other in a joint if the capacity that is required exceeds the 195 kilonewton. And we have come up with some spacings between the items that are required, spacings between the connections that are required to get the full capacity in different panel thicknesses. We are restricted to panels that would be 200 millimeters and above. We have seen that this is the area where these kind of loads are also required, so it fits quite well. And we have here a table which shows different capacities for smaller spacings. So if you're increasing the concrete strength, you could in theory increase the capacity. But as our tests have only been done in a 200 millimeter panel and we achieved the 195 as a characteristic capacity, we don't really want to go higher. We will talk later. The project is ongoing and we might do a little bit more testing, or we're also working on finite element designs right now to have maybe less conservative approach to give out capacities. At this point of time, our capacities here are very conservative. Like I mentioned during the video, we need some reinforcement bars. So on the right side, you see in blue a U-bar above and below each of the connections, and you see two perimeter bars, which is what we need to take over the loads. In regards to adjustability, the opening that we have allows us a vertical adjustability of plus minus 25 of the overall connection, and horizontally 15 millimeters of the overall connection, which means each of the items can be placed 12.5 millimeters in the heights, plus minus 12.5 millimeter in the heights up and down, to still work out if you had the maximum displacement to the top in the one direction and the maximum displacement to the bottom in the other element, it would still work. And 7.5 millimeters in regards to the panel thickness, so plus minus 7.5 for each of the two items. Here our typical cross section would look like. That's a 200 millimeter panel having our S connection in it. At the top, you see how before the dowel is actually sliding over, how the dowel is parked in the male part. At the bottom, you see when the dowel is slid over and the panel is, or the connection is filled with grout. And on the right side, you see how I mentioned before, there is also a corner connection possible. In this connection, then the grout opening is in the same surface as the opening for the S connection, so that the grout connection can be reached later on too. Here's some shots from panels that were cast in a precast yard to see how it actually looks like in a panel. Here are some more, and here also some very large panels installed. You see in this panel, for example, we have 6 connections over the entire height of the panel because this was required by the engineer to take over all the loads. On the left side, this is a corner connection again, so the other panel will go towards the face of this panel. Here from Victoria, some images from data center. Data centers work. We have made it work, but they have very high reinforcement in these panels. So we see there that it is almost a struggle to get anything, any connection in, and no matter what kind of connection it is. Here's some more shots from that job site where you can see on the right side here before the dowel is actually moved over how it looks like, and you couldn't pull it over once the other panel is next to it. That's why we came out with this rope solution where you're pulling the rope and it comes over. From a commercial point of view, we had so far 15 projects throughout entire Australia, including of all places Darwin. We normally travel out to the precasters for the first use to make sure everything runs smooth, and so that we can bring our experience from other projects in to make sure that the precasters that first want to use this product are successful with it. And here is feedback from one of the projects in Melbourne, where the capital group that used the product had a very positive feedback about the cost savings that they had all in the project. They saved 40% of the total cost compared to wet joints that they would have normally used. They say that normally 5 workers would work around 5 hours to finish a single floor and do all the wet joints in there. And now they only needed 1 worker for 2 hours. So it's speeding up the construction process. It's bringing better quality control, and it's overall cost saving and making less high risk work on a job site. And we're moving more work from the job site to be done off-site where it is better controllable, and we are promoting precast with this kind of solution. So that's it from me. I'm happy to pass over back to Arun, I think, and then to Scott.
Thanks, Andreas. That's a fantastic presentation. It's like the perfect foundation for Scott to build on. So, not taking a lot of time, I'm introduce Scott. Who I'm proud to call my friend. Scott is a senior lecturer at Swinburne University of Technology at the Department of Civil and Construction Engineering. He's also the president of the Australian Earthquake Engineering Society. Scott got his PhD from Swinburne University. He was the joint inaugural recipient of the prestigious Dr. William Piper Brown AM Scholarship. Scott is a chartered professional engineer and has experience designing building in the health, government, education, transport, and residential sectors. His primary research interests include reinforced concrete, precast concrete, earthquake engineering, and collision actions. Scott is a member of BDO 611 and BDO 208, which are the Standards Australia subcommittees responsible for AS 1170.4 and the seismic provisions of AS 3600. And Scott was chief editor of the recently revised commentary to AS 1170.4. His other research outputs include textbook titled Collision Actions on Structures. Over to you, Scott.
Thanks, Arun. Thanks for the extended bio. Quite long in the tooth there, but all good. Thank you. Thank you, Andreas, for providing the first presentation and overall introduction to the project. So today I'm going to have a bit of a chat about some of the work we've been doing at Swinburne in the precast connection space to support the research efforts being driven by PSA. So just a few acknowledgements, obviously, to kick things off. Smartcrete are funding a lot of this work, so thank you to Smartcrete and PSA, and then also to our team here at Swinburne. There's a few of us working on different parts of the project, so just an acknowledgement to the Swinburne team as well. So today I was just going to have a few brief words about the PSA Swinburne collaboration, and then really have a talk about the vertical and horizontal connections that we've been looking at as part of this project. So the PSA Swinburne SmartCrete CRC collaboration, this was really a collaboration that was about 5 years in the making, and it was really off the back of 5 previous that I would call successful research projects together. And so, as part of these previous research projects, we were looking at early versions of the S connection that Andreas looked at or presented on. Also testing on various precast components, headed inserts, and looking at grout tubes and all a range of different products for the precast market. And then really on the back of all those previous projects we did together, that's where we kind of ended up with the SmartCrete project that we're talking about today, which is next generation precast concrete wall and column connections and design procedures. So yeah, it's been a long collaboration in the making to get us to here, and we've had some good results along the way. So when we talk about prefabricated wall systems, I think it's sometimes good to just take a step back and have a bit of a snapshot of what we're looking at, so everyone's on the same page. So really, we're looking at concrete walls or cores, mostly cores. And when we have a precast core, we typically have 4 individual panels that we join together on site to create our 4-sided box. Then we have grout tube connections, and we have panel-to-panel connections, which historically have been largely dominated by stitch plate connections in the industry. So when we talk about when I talk about vertical connections, we're really talking about the panel-to-panel connections like the stitch plates, and then when we talk about the horizontal joints, we're talking about the grout tube connections. So for in the vertical connection space, this is really where we're looking at the S connection. So as part of the previous work we did with PSA, we developed the first generation of the S connection, and that really led into the work we're doing with SmartCrete now to look at the use of the S-Con in more configurations, more panel thicknesses, concrete strengths, as well as looking at a higher capacity version in general. But as Andreas presented previously, this is just another diagram of the S connection where we have a male end that extends out and into a female end in the other female insert in the other panel. And so when we were looking at the development of this connection, we did look at testing in a number of different directions. So we did vertical in-plane shear testing. We did outer plane, so kind of a vertical in-plane shear testing. We also did outer plane shear testing, and we also did axial tension testing. Now, with these connections, the primary application, and when I say primary application, it's really what they're doing 90–95% of the time is really these connections are being used to develop composite behavior in the lift core. We're trying to get, as I said before, we're trying to get 4 individual panels to work together as one 4-sided cross section, and to do that we need to transfer vertical shear. So that's why the primary loading we're looking at is this in-plane vertical shear, because these connections are allowing those individual panels to act as one box. So while we did also do outer plane and axial testing, we just didn't do as much compared to the in-plane vertical, because that was the primary thing we were looking at. So as part of that connection testing in the round 1 testing, we've got a slightly different setup for the work we're doing now. But essentially we had this setup here where we had a panel on the left and a panel on the right, more easily seen in the diagram here. And essentially what we were doing is the panel on the left was fixed at the bottom of the machine. The panel on the right was pushed up, or we applied cyclic loading, so we pushed it up and pushed it down. And then we used some structural steel to kind of restrain that panel rotation to try and get perfect shear across that connection. Perfect shear is actually quite a somewhat difficult type of loading to apply to a connection. But this was the kind of approach we went in the first project to try and apply that perfect shear across the connection. So really, hold those two panels straight and move one side up and down to look at that capacity under reverse cyclic loading. So that was the testing that we did previously on the first generation of ESCON that really led to the capacities that Andreas was talking about previously. However, as part of the ongoing development work in the ESCON space, we're really looking at trying to understand how it performs in a much wider range of scenarios. So as part of that, we have some work looking at developing nonlinear finite element models of the connections. This work's been led by my colleague, Dr. Zhanji Wang, and so we're really trying to develop some fairly complex and detailed nonlinear models of these connections, so that way we can try and understand their behavior over a wider set of variations in panel geometry iterations, because the reality is when we're talking about precast, full-scale precast connections like this, it's kind of impossible to do a test program where you look at every single iteration like you may do for smaller components like ferrules. So really what we're looking at is we're looking at really driving, we're having baseline capacities driven from comprehensive experimental testing, and then developing strength modification factors determined from the finite element modeling. And this is kind of like what some of these models look like below here, but this is still a work in progress at the moment. But as you can see, from these models, they're quite a detailed model. It's not the typical sort of finite element model that you produce in a design office. It's very much a micro, detailed model where all aspects of both concrete and reinforcement non-linearities are considered. So another major component of this work is horizontal connections, so really looking at grout tubes. So PSA have their plastic grout tube system, which is essentially a corrugated grout tube blow molded, produced via a plastic blow mold. And so one of the big advantages of the PSA grout tube system is the ease of construction, and that's really the feedback from a lot of precasters, is they want to use it because it makes it just easier to build these elements in the factory. So as a result, we've been working with PSA to do a number of different types of testing on this system. We've looked at pull-out testing, fire testing, and also looking at more recently some durability testing to understand the long-term performance of both the plastic grout tube and conventional spiral duct. So the pull-out testing, just a few photos here where we're just looking at more conventional pull-out testing to understand how the connections behave, and so essentially we have reinforcement with threaded inserts that we hold the panel at the bottom and then essentially pull the bar from the top. And as part of this work, we've had a number of different specimens. So we had specimens with kind of very short grout tube lengths to understand the isolated bond behavior of the grout tube, and then kind of having full length grout tubes to kind of understand the overall connection performance. We also had a look at fire testing. So this was using one of our fire testing facilities at Swinburne, where we have a vertical furnace where we can apply fire heat loading from two faces. So this is just looking at what these panels look like when you open up the furnace. As you can see, the concrete gets fairly red hot. And then we did both, after the fire test, we did both pull-out testing. We also had a look at some retrofit details where you can as you can see, the panels get quite bashed up from the fire testing. So we looked at also some retrofit details where we can kind of patch some of the cracks that develop with epoxy crack injection, and also doing pull-out testing after the fact as well. This is also, work that's in progress, is still in progress as we present today. And the final thing we've been looking at in the grout tube space is durability, and this is kind of a bit of an interesting one. And this is being led by one of our students here at Swinburne, Arifullah. And he's really looking at a really comprehensive durability assessment of grout tube connections, where he's looking at both plastic, the PSA plastic grout tubes, then also looking at the conventional metal spiral duct grout tubes, because there has been some work out of the US that's shown that the spiral ducts, even though they're a galvanized product, because the metal's so thin at about 0.5 millimeters, as soon as you get any sort of corrosion ingress in there, you can actually get these tubes rusting out in less than 10 years. So that's quite a concerning bit of research that was done 5-10 years ago. So we're kind of just trying to understand that a little bit better as well. And then as part of that, we're also looking at different grout types, type A grout type, type A GP grouts versus type C high strength grouts, and also different grouting techniques, dry pack joints versus liquid grouting, because as you can imagine, depending how well the joints are grouted will affect the the pathway for corrosion to ingress through. So we've got two different techniques being adopted. We've got chloride testing and carbonation testing. For the chloride testing, you can see these are the specimens here, where you can see this is the kind of grouted joint here. There's a bar going through the connection, and then you put the salt solution on top. So essentially, this is a long-term test. We're only a few months in, but this is going to be going for at least 12 months. And we're going to monitor the corrosion as it goes. And then after do the testing, we're going to cut the specimens in half and do a pull-out. We're going to cut the specimens in half, have a look at any corrosion, as well as do a pull-out test to see if the pull-out capacity is affected by any corrosion observed. And we also have some baseline specimens that have no chloride on it. And then we're also looking at carbonation testing, where effectively doing something similar, where putting some specimens in the carbonation chamber and looking how that affects the corrosion of these grout tubes and whatnot. And so essentially we start with the carbonation. We start with quite a large specimen, and then as we kind of progress, every 3 months through the program, we actually kind of cut slithers off the end of the specimen, so that way we can see how the carbonation is kind of tracking through that horizontal grouted joint in the specimen, which is really the weak link of the connection. And then just to wrap things up from my side, I just wanted to promote to everyone that in November this year, we're having a prefabricated concrete workshop at Swinburne. And so this will be a workshop/seminar, which will be a mechanism to bring researchers, design consultants, and prefabricated concrete specialists together to present ongoing research initiatives and state-of-the-art best practice. And we really want to kind of bring the designers, the contractors, and the precasters into one room, so really everyone can kind of hear where each other's pain points are. Because often, one of the things that I've found interesting is, particularly, coming from a design consultancy background, is when I was working as a designer, you're working with a certain set of parameters, and when the project gets to the precaster, it's very difficult to change things for a number of different reasons. And then through the work I'm doing now and engaging with precasters directly, you quickly learn there's certain things you can do from a designer's perspective that cost you nothing if implemented at the right time, that can make the precaster's life a lot easier, which ultimately will result in a better product. So part of this workshop is also trying to just get different people in the same room who wouldn't normally be in the same room to share experiences. So this has been hosted at Swinburne. It's on Wednesday, the 19th of November. We'll have a registration link distributed via various channels in the next few weeks. We'll probably get Smart Creek to send that around for us as well. But if you don't see that, if you don't see any advertising and it's something that you're interested in attending, please feel free to send me an email directly. My email is also on my Swinburne profile page. You can just kind of go Scott Menegon Swinburne into Google, you get to my Swinburne page, and then my email address is there as well. If you don't see it and you want to would like more information or would like to attend. And with that said, that's all from me. Thank you, Natalie, for organising, and thank you, Arun, for hosting. And pass it back to you, Arun.
Thanks, Scott. I remember we spoke about the workshop sometime last year, and it's really good to see it's coming together, and it's happening this side of Christmas. All the best and good luck with that, and a great presentation. Thank you so much. And we are opening the floor for questions. But Jeff Fletcher had 2 questions in already, so we can start with that. I think the first question is for Andreas. Can the dowels be overextended? The red marks indicate that the dowels are fully extended and must be observed.
Thanks for the question, Jeff. No, when you pull the rope, the dowel goes all the way to the end, so there can really not be an overextension. If you pull the rope all the way, then the dowel will be it's just making sure that you pull the rope long enough that it really goes all the way over, but an overextension is not possible.
Another question from Jeff. The plastic used for the blow molded ducts and S connection, does it soften, melt when at elevated temperatures related to steel and concrete fire behavior, say 250 degrees Celsius?
Yeah.
I'm sure Scott. Scott has an opinion on this. Okay, great. Yeah, Scott, go ahead.
Yeah, no. So I think it's a good question. So what we've looked at so far is really trying to understand the kind of ultimate behavior. So under quite severe fire loading, you do get the plastic melting, but because the grout tubes have such a large, I guess, mechanical interlock, because the ribs on the grout tubes are really around 8 millimeters deep compared to a spiral duct, which is maybe nominally half 1 millimeter. Sorry. Because of that kind of quite large mechanical interlock, you still get close to 500 MPa worth of bar stress as a post-fire capacity. Then what we're really looking at is, well, what about if you look at the state of those panels afterwards? Obviously you're never going to leave a panel like that. So if you then do a retrofit epoxy crack injection, what happens? And you get back to full bar break capacity. So then really, I guess your question, Jeff, is really, what happens in the in-between state where you have elevated load, but maybe not enough to fully, and high load, but not the kind of full ultimate fire scenario. And so, we're still working through that. I'm not going to say we have a definitive answer for you here today, but the kind of working assumption for what we've observed is that, for that grout tube to melt, you kind of need severe cracking and spalling of the section. Otherwise it's kind of trapped in there. And so, the fact that the specimen needs to get badly damaged for it to melt is then also the kind of cue after the fire to say, hey, we need to fix this. Because, if you have a look at the concrete, if you look at the concrete adjacent to the grout tube connection after the fire, you can clearly see that it's cactus and needs some sort of retrofit performed. So that's the kind of working assumption that we've been able to observe, that really, for there to be a problem, the concrete needs to be in severely spalled and cracked, which is then a kind of visual cue to do something. So, but we're still, working through that firework.
Thanks, Scott. Go on, Andreas.
Sorry. I would just like to add that with the injection molding, we actually have the chance here to do something that has significantly bigger ribs, and Scott already mentioned that, compared to the spiral ducts. So both the S connection and the grout tubes, the plastic grout tubes, they have really significant ribs, and this really helps to take the loads over. And if really in worst case, the whole plastic would melt away, you would have some slip, but you would still have a good load transition. And these items are also sitting normally centrally in the panel, so they have a lot of protection until they really get the full heat. And you would probably have bigger problems with the reinforcement in the panel itself, which is much closer to the edges of the panel and gets higher strengths. So yeah, we're still ongoing testing there, but we really think we have a good solution here also for fire.
That's a good segue to the next question for both. So Nan Zhang from Swinburne asked, when testing the bond strength, did the plastic grouting pipe damage first? And the second question is, how about the requirement for strength of grouting concrete?
Yes, I mean, in terms of the bond strength of the grout tubes, so for the plastic grout tubes, you know, when we did the pull-out testing on the plastic grout tubes, effectively what we found was we couldn't get the bond between the grout tube and the concrete to fail. And you know, it's really a function of the fact that you have, you know, despite you have, you know, plastic, despite there being a layer of plastic between the concrete and the grout, because you have such a large interlock, you know, you have a good 8 millimeter deep rib, we could never actually get the grout to concrete interface to fail. What we always ended up getting was the you know, the bar to grout interface failing. So no matter what sort of you know, length, bar diameter, like embedment length, bar diameter, grout tube ratio, no matter what set of test parameters we looked at, whenever we got pull out, it was always the rebar to the grout, which is not necessarily you know, surprising considering that you know, if you look at the area between the bar to the grout, it's much smaller than the grout to the grout tube in terms of bond area. But it is still reassuring that no matter what we did, you know, essentially put a really big bar in a small grout tube, you know, you just can't get that kind of interlock to fail, which is positive. And then in terms of the grouting, you know, so we were generally looking at a fairly, you know, for the pull-out testing of the grout tubes, we're really looking at a fairly modest grout because, you know, we could put in super high strength grout, but then that becomes very expensive. And people like Arun over at Advanced Precast go, mate, we don't want to use your product anymore. It costs too much per bag. So we're really looking at just a good quality GP grout, something that is, you know, cost competitive. And that's what we use for that pull-out testing. But really as part of that work, another part of all this work that we kind of, you know, have been kind of lifting the lid on is really the performance of grout in general, where you know, some of this precast work we did with PSA, you know, in one set of testing we got some surprising results, and then when we unpacked it, it was because the commercially available grout we're using, you know, essentially came in at 50% below the advertised capacity. And so as part of, so that was quite early on in our research collaboration. So, but that kind of finding kind of also led us down here at Swinburne has led us down a parallel pathway where we've been testing, you know, many different commercially available grouts and finding that, you know, essentially not all grouts are created equally. And, you know, the kind of attention that needs to be given to grout specification is grossly not where it needs to be by the industry, to be frank. And so this is something that we're now kind of engaging with National Precast to try and hopefully put together some industry guidance notes to kind of help push people in the right direction in terms of what they need to be thinking about in terms of grout selection and grout specification.
Thanks, Scott.
Just adding, just adding for the S connection, we have a special grout, so we call this the PSA connection grout. This is the grout we tested this with, and this is also the grout we would recommend for everybody to use, so that we make sure that we get the full strength. So for the grout tubes, it's a different thing. We don't want to really have, you know, just one grout out there, but for the PSAS connection, it was tested with one specific grout, and we would always strongly recommend that people get that grout from PSA.
All right, thanks, Andrea. The next question is from Adi from Advanced Precast, who has better say than me in which supplier to choose. The question is, are the capacities of the S connection expected to be lower when used in the corner scenario?
No, we have the same capacities in the corner scenarios here than compared to what we have in the panel-to-panel end connection. Yeah.
And really a part of that is because the geometry of the S connection was really set up around working in both a kind of straight panel connection and a corner panel connection. So we kind of, I guess we kind of, you could say we kind of, the capacity was in some respects limited to the corner scenario, as opposed to kind of being optimized for, say, a straight panel connection.
Thank you. I have a couple of questions from me, and I read all your bio, Scott, in the beginning because I had this question coming because you have been in and around all the standards committee and been actively involved in writing standards and you are being an academic yourself. So, how do you think the standards accommodate these new connections? And me coming from a concrete background, we always say it's a slow process, but how, and being from both sides of the fence, how do you see the standards accommodating these state-of-the-art connections?
Yeah, I mean, I think when you start exploring this space, you quickly see the holes that are in our standards or the shortcomings. And when you particularly when you develop a new connection and designers, you present it to the design community and designers have questions and rightfully so. But then the interesting thing is, the questions they have often also highlight deficiencies and shortcomings with our current design approaches for precast connections, where there really isn't any guidance in Australian standards. So it's an interesting space where we have a kind of established precast design or precast industry in Australia for in the building space, let's say, but and we have these kind of conventional connections that everyone's comfortable with, everyone specifies. But then when you really drill into it, our standards don't really support, the design of any of those connections. But people have kind of become comfortable over time and happy to specify it regardless. So then when you develop something new, while there aren't design procedures in the standards for these connections, they're equally at zero design procedures for stitch plates. So I guess one of the big differences is at least we've tested this, and when you look at 3600, particularly the 2018 version, they made an attempt to include an appendix on structural testing. So at least, and they included an appendix on structural testing, which was really an attempt to provide a deemed to satisfy avenue for people to rely on test data for kind of these bespoke connections, and without something like that, I think it will become quite difficult. So that is one positive change. There's always an appendix, a testing appendix in the 1170 series of codes, but I think just seeing it in 3600, I think just mentally provides such a different sort of signal to the industry, and also makes designers feel a lot more comfortable. So yeah, it's definitely a hard space because I don't think our standards can ever fully cover, what we're doing in the precast space, and ultimately relies on engineers to make engineering judgment as much as a lot of people are risk averse these days and don't want to do that. So yeah, no good answer for you there, but it's tricky is the long and the short of it.
Yeah,
I guess the other thing to note there as well is I tested some welded stitch plate connections probably 6-7 years ago now, and prior to testing those connections, actually went out to 5, 6, 7 major consultants and said, "Oh, look, blind prediction, try and work out the capacity prior to the test." and there were some consultants that got pretty close to the mark in terms of saying what the capacity would be, but equally the kind of blind predictions varied by, it went from 50% under to a factor of 2 over. So there's a kind of factor of 4 in the capacities that people are assuming for these connections, essentially. So kind of highlighted the even before we start talking about kind of new connections, even with conventional construction, there's a huge amount of uncertainty in the industry.
Yeah, so it's a very good point that Scott is making here, because some of the established connections, or however we want to call them, are not very well understood in the community, and sometimes it feels like a lot of designers copy and paste standard details from projects without really fully being aware of what the loading situation is and what the capacities of these items are. And I think that's why here the project has taken the right approach to take somebody like Scott on board and work together with Swinburne, because they have the experience from other connections and they can find a meaningful test program so that we can come up with capacities that people can believe and can back it up with the right testing program so that we can all feel comfortable about it. But not everything can be covered by standards. Otherwise, we're ending up with huge standards that nobody understands. So we need to still trust the people that test and develop these products and come up with these solutions, and we need to trust the people to specify them later on, to be good engineers and to understand and read the documentation that is available.
One of my go-to thinking is that the standards are byproducts of what's been happening in the industry in the past 20 to 30 years, not what should be happening in the next 20 to 30 years. And I mean, they very much aligned with the same sentiment with you guys.
And I guess, sorry, just one more thing to add there. I guess, everything we spoke about today is, really the kind of R&D work developing the PSA connections. But I guess as part of this kind of larger Smart Creep project, particularly on the Swinburne side, there is a kind of, I would say, there is a kind of another part of the project which is going to kick in, the kind of second half towards the end of the project, which is really looking at, preparing some design procedures, both for these new connections and also for conventional connections. And I think, that work, developing some design procedures, which we're engaging with National Precast for, I think will help provide just a bit more transparency in this space. So that way, while it's not necessarily a design procedure in the code, it is a kind of, a design procedure that's kind of, an industry design note, sort of, an industry-backed design procedure, shall we say.
And then there's another question from Son in the chat. In the context of low carbon concrete, is it widely adopted in precast industry practices? Maybe I can add a bit more to that question to you two. So there's a lot of work happening on the sustainable concrete side of things, where I am mostly from. But when you test for pull-out testing and the grout tubes and so on, and then this is a question that I always want to ask from a structural engineer while I am on the other side of the fence. And do you account for all these new sustainable concrete materials and the low carbon concrete that comes through?
Yes, I guess the main it's a good question, because when we do our testing, we're really just looking at conventional concrete. Now, conventional concrete these days has a fair component of cement replacement materials. It's almost impossible to buy concrete these days. It's just 100% Portland cement. So there is, a little bit of, I guess, cement replacement in there, but it very much is kind of conventional concrete. My suspicion is, as long as the compression behavior, tension behavior, and bond behavior is similar, then everything else should more or less be the same. But it's a good point you raised there that that's probably one thing that I haven't seen too much of is, looking at that, comparison at a structural level to verify that we're not getting changes in behavior. I wouldn't have thought we would. I wouldn't have thought so, but it's probably an important piece that needs to happen at the more kind of general, at a more general level.
I mean, for connections, we're always referring back to the compressive strength of the concrete, and what really is required is the tensile strength and the breaking energy of the concrete. So if the ratio of any concrete between the concrete compression strength, the tensile strength, and the breaking energy is similar to a normal concrete, I would expect that it behaves the same. But I also saw Jessie Lee is in the room, so maybe she can take that to the next AFAC meetings and bring that up as a topic. I know AFAC has done a lot of work in regards to low strength concrete, high strength concrete. Maybe they also need to look at the more innovative concretes that are out there and see if all the methods for anchors and connections still apply to this. It's maybe a good topic for Jessie to take with her. Hope she hears me.
Thank you.
Yes.
Professor Wood Professor Wood has his hands up. Yes, over to you.
Yes, thank you. I just like to contribute to this particular discussion a little bit. I guess there are two broad classes of low carbon concrete. One is that of the concrete with SCM, different level of SCM. The second, obviously, is the alkali activated biosystem or geopolymer concrete. On the first system, concrete with SCM, I think for precast work, mostly people would not use concrete with high SCM content, mainly because of the early strength requirement that is quite important for precast casting and so forth. So I don't think that would be a big issue for low carbon concrete with high SCM content. On the other hand, on the alkali activated biosystem, I think technical specification 199 did go into a lot of details similar to 3600. So I think that class of low carbon concrete is reasonably well taken care of by technical specification 199.
Thanks, Professor. And like everywhere, the concrete people have hijacked the engineering design aspects of this event. But this was a great discussion towards the end. Thank you to speakers.
Can I say just one more
Yes,
note,
go
Arun, as well?
on, Scott. Yeah.
I think just one of the other things it was kind of Andreas kind of opened up the conversation there, and it's a convenient lead into an adjacent smart grid project that AFAC actually has that's kicked off in the last kind of 6 months. Looking at low carbon anchors in low carbon concrete. Well, it's actually there's kind of two projects. One's kind of led into another one. So yeah, there is actually some work looking at as Andreas mentioned, there's actually an APAC project with smart grid looking at that. So it's a kind of adjacent bit of work that's hopefully answer some of those questions.
Yeah. As we speak, Jessie just put that in the chat too. So it was good, really good that you are already looking into that and the great work that's happening in the space. And we are definitely running out of time, and Natalie is going to come after me. So probably time to close our session. Thank you to all the presenters for speaking and sharing the thoughts in and around the industry. And all the best for the rest of the research and using it in the construction sites. It's always hard work, but good luck. And for any follow-up questions or collaborations, reach out to Smart Grid CRC. We'll make sure your messages get through to the right people, and then you'll get answered. And it's from us today. Thank you for being a great community, and enjoy the rest of your day. Take care.
Thank you, Arun. Thank you for the great presentation.
Thanks.
Yeah, thank you.
Thank you.
Thank you.
Thank you.
Thanks, everyone. Bye.